Good day, everyone. We're reviewing Wetzel's Limnology textbook, edition number 4, chapter 4. And yesterday we focused on lotic ecosystem, which means flowing water ecosystem. And today we will be focusing on drainage basin characteristics. And before we embark on doing so, let's review a couple figures and tables. So the first one is this table here, tables 4-3. Drainage network characteristics for river reaches from the River Atlas version 1.0 database. River reaches are here defined as sections between two confluences or between the initiation of a stream and the first confluence. So on the left, we have the mean discharge in meter cube per second. We have then the number of river reaches, the total river length of our reaches in kilometers, the average upstream drainage areas of our reaches, the average elevation, and the percentage of non-perennial reaches. So what we see right away is that there's a high number of river reaches with a small discharge, 3.9 million reaches, with a discharge between 0.1 and 1 meter cube per second, representing 15 million kilometers of river length, and an average drainage area of only 90 kilometers squared, with an average elevation of 604 above mean sea level, meters above mean sea level. And then percentage of non-perennial reaches of 47%. And then so if we look at the bottom of the table, we have, like in that case, 360 river reaches exceeding 100,000 meter cube per second, representing only 1,319 kilometers of total length of rivers. An average upstream drainage area that is huge, that is 4.5 million kilometers squared, with an average elevation that is very low of 7 meters above mean sea level, and 0% in terms of non-perennial reaches and the percentage of the length. So that explains it a little bit more here in figures 4-6. So figure 4-6 looks like the geometry of a typical river from the upper reaches to the estuary, and then looks at the behavior of some parameters, some hydrologic parameters. So let's first look at the geometry of that river. So in the upper reaches, we have elongation phase, valley deepening. Middle reaches, we have rebedding with the presence of gravel banks. In the lower reaches, we have meandering with lateral erosion and stagnant water. And then ultimately, that reaches the estuary. So we have two parameters that are increasing from the upper reaches to the estuary, the discharge rate and the annual temperature. And then we have two parameters that are actually decreasing from the upper reaches to the estuary, the oxygen and the flow velocity. Drainage basin characteristics. The drainage basins or drainage area is the area of land drained by tributary streams that coalesce into a main channel. Note that whereas the general term drainage basin is used here to describe any size of drainage area, for example, from small headwater basins to large river basins, hydrologists commonly use the equivalent expressions catchment or watershed, mostly in North America, when referring to small or medium-sized drainage basins. Usually surface features, topographic divides, are used to define the extent of drainage basins, although subsurface flows may have different boundaries, phreatic divides, particularly in areas underlain with relatively soluble or permeable rocks, such as, for example, karst. The world's largest drainage basin is formed by the Amazon River and its tributaries, reaching an area of about 6 million kilometers squared. Drainage basins can be subdivided hierarchically into subbasins where each tributary forms its own nested drainage basin. The continual downgradient movement of water, dissolved substances, and suspended particles in streams and rivers is derived primarily from the land area draining into the stream channel. The hydrological, chemical, and biological characteristics of a stream or river thus reflect the climate, geology, and vegetational cover of its drainage basin. These specific characteristics can be used to highlight similarities and differences between river systems and classify them into river types. The spatial and temporal patterns of stream flow or discharge are governed by the hydrological cycle. Discharge Q is defined as the volume of water passing through the cross-sectional area of a stream channel per unit time and can be calculated as Q is equal to AV, where Q, discharge in meter cube per second, A, cross-sectional area of channel in meter squared, and V, mean velocity in meter per second. Discharge can vary greatly from season to season and is directly related to the extent of the drainage basin and its characteristics. Given these relationships, landscape characteristics within the drainage basins are often used as initial descriptors of possible hydrological behavior, including variables of physiography, for example slope, climate, land cover, soils, and geology, as well as geometric features of the drainage basin, such as elongated versus compact shapes. The length of the main channel, LC, increases in a relatively constant way with drainage basin area, where LC is equal to J A to the M, where J and M are derived from many measurements and average about 1.4 and 0.6 respectively. Thus, as drainage basins increase in size, they tend to elongate. Drainage network patterns. Several methods have been used for ordering the tributary streams in a drainage network. In the classical stream order system, also Hack's or Gravelius stream orders, order 1 refers to the main stem or backbone river that drains into the ocean, and every tributary is numbered one order greater than the respective river or stream into which they discharge. Other systems have been developed that rank streams from smallest, first order, to largest, highest order, including those by Horton and Shreve, etc. In the most widely used Streitler method, the smallest permanent stream is designated as the first order, and the confluence of the two first order streams create a second order. The order then sequentially increases by 1 when two tributaries of equal order meet. Using this metric, the number and total length of streams within a drainage basin can be statistically estimated. Deficiencies such as scale dependencies in these popular methods of stream ordering, as well as alternatives, are reviewed by Gordon et al. More recently, scale-independent ordering systems have been proposed that assign streams orders based on mean annual discharge. Many patterns of channel networks are observed. These patterns depend on geologic structure, rock types, tectonic activity, presence of faults, landform shapes, and exposure to climate and vegetation. Dendritic channel networks typically develop in relatively homogeneous geology or where geology exerts less control, while non-dendritic drainage patterns, for example trellis, occur in areas underlain by different lithologies and tectonic activities.